Hello, my name is David Swoboda. I'm a software security engineer with the SEI, and I'm here to talk to you about the automated repair of static analysis alerts. So I'm going to start off with a quick overview of static analysis and its use in the DoD. Static analysis, of course, is the attempt to discern information about the security of a program or its style or its correctness without actually running it. Everything you can do short of running the code is covered by static analysis. And the first question is, does the DoD require you to use static analysis in the code you develop? And what I have here is some quotes from the ASD STIG and from NIST. The long and the short of it is, if you don't know anything about whether you should be using static analysis, the answer is you should. If you are familiar with static analysis and for whatever reason you hate it, then you can probably avoid using it for a few more years. I suspect over time this text will get stronger and you will eventually be required to use static analysis. And this presentation is directed at people who are using static analysis. So the good news is about static analysis is that it finds lots of true positives, things that are definitely true about your code and that need to be fixed. But it also finds lots of false positives, things that are not really true about the code. There are limitations, you might say bugs, in the analysis tool. And we are focused on both of these problems, the problem of true positives and the problem of false positives. Fundamentally, there are, by most static analysis tools, too many false positives to audit them all. Someone has to sit through and manually say, this is true, this is false, this is true, this is false. And even when that's done, there are still too many true positives produced for the average C and C++ code base to audit them all or to fix them all. So two separate problems. So our proposed solution is to repair the every static analysis alert. We will build repair algorithms that repair 80% or more of static analysis alerts in each category for the code bases that we're working over. We'll build this for three types of problems in the first year, and for the next fiscal year, we'll extend that to 10 types. So let me go a little bit more into the, the particular problem, which I call the deluge, because anyone who's worked with static analysis tools on C and C++ code will know this. Our experience at CERT has been that static analysis tools are very prolific with alerts, and they can produce one alert for every 3 lines of code. That's about 350 alerts per 1,000 lines of code. There was a recent study done by Google and Bill Pugh of FindBugs fame that discovered that on the average it takes 117 seconds to audit an alert, that is, determine whether it's true or false. And if you assume also that it takes another 117 seconds to fix the problem, then the average C or C++ code base is 2 million lines of code, roughly, and it would take a single person 3.43 person years to audit all of the alerts and then repair just the true positives. 3.5 years for the average code base. That's a lot of effort. I don't know anybody who actually does that actual work. In addition to the amount of effort, it's simply tedious. We've talked with our collaborators, and according to them, first of all, they note that C and C++ code tend to have the most number of vulnerabilities, more than Java code or Python. And so C and C++ code is in the most dire need of static analysis. Fortunately, well, what our collaborators tend to do is to focus on a handful of the most critical CWEs, alert categories. They focus on 30 CWEs. They ignore any alerts that are not in those 30, and those 30 are things that tend not to produce lots of alerts. This makes the deluge manageable. They've basically ignored most of the deluge and just focus on critical problems. Consequently, they analyze about, they find that about 20% of the alerts they find are true positives, and they fix 90% of those true positives. So, as you might guess, this was not a surprise to me. What was a surprise to me was that we proposed building a nice graphical interface to our repair tool that would make it easy for them to see how the alert can be repaired. And they said, that's nice, but what we really want is a continuous integration pipeline. we want to add your tool into our CI pipeline, which will streamline the problem and make it far easier to solve. Well, we're very big on continuous integration here at the SCI, so I said, fine, we'll do both, but we'll prioritize the CI pipeline. I'll come to that in a little bit of how that will work. So the current state of the art with code repair and refactoring is that refactoring code has been available for Java for 20 years. Eclipse is an open source Java interactive development environment that provides repair and has done so for 20 years. However, the work of repair in C code has been all confined to the research community. There are plugins that have been developed for Eclipse's CDT for developing C and C++ code, such as for repairing integer overflows and buffer overflows. There are also plugins, there are refactoring plugins for Microsoft Visual Studio Code that will also do code refactorings, that is automatic rewriting of C or C++ code. As far as we can tell, they have not extended them to doing fixes for security problems, such as what we're proposing here. I would also give a shout out to Dr. Will Kleber, who will also be presenting a separate project, but he has run a research project in the SCI from 2017 about automated code repair, and he is one of the giants whose shoulders I am standing on for this project. So a lot of what we do is built off of his work. Furthermore, there have been developments and refinements to Clang, where Clang, the compiler Clang, now can produce an abstract syntax tree data structure and serialize it into JSON. And this allows us to slurp up that JSON and analyze it using whatever language we use. We don't have to use C++. In the past, all static analysis I've done has had to be done in C or C++. And so being able to do it in Python, or whatever language you want, is a great boon of freedom. And therefore, I think this is the time to start focusing on automatic repair. So, what's our solution? There have been automatic repair routines that modify a huge code base, and the problem with that solution is that you have to do everything right. You can't just do 90% of the repair job and finish. It has to be 100%, or the code is broken, it doesn't work. We're taking a different tactic with this project. We are instead focusing on individual small repairs, such as the example you see down here. The concern being that if the sum of the two numbers wrap, they cannot be, then undefined behavior can result, and lots of things can go wrong. So we just simply add sufficient checks to make sure that the addition cannot wrap before we do it. Along these lines, all of our repairs will be small and cheap. If you had, say, 100 integer overflow potentials like this, you could fix them in 100 places. This is tedious for a human to do, but would be very easy to do automatically. So there's two fundamental aspects with our repair, actually three. First of all, we're not actually doing our own static analysis. We're assuming that you have another static analysis tool that will tell you if there's a potential integer overflow, and we let the tool decide, which things we should repair and what part of code we should leave alone. Secondly, we want our repair to be sound. We make sure that a repair will not break the code, whether or not the repair is a true or false positive. And thirdly, if the code is a false positive, doesn't matter, we're going to repair it anyway. We trust the static analysis tool, and we are focusing on repairs where repairing a false positive does not break the code. We also have the notion that we shouldn't repair code that we've already repaired, so we have to do enough static analysis to make sure that the repair is indeed a false positive. And as you can see, most of our repairs will be simply wrapped up in this little macro like safe add. So this is the picture of how static analysis is traditionally done, and how our repair tool is going to be integrated with a static analysis with a GUI. In this case, the user simply works with their laptop. They're using an IDE like Eclipse or Visual Studio. And the IDE they also have a static analysis tool available that can produce alerts. And the IDE can show the alerts that are produced by the analysis tool. And the user is therefore required to go through the tool, the elements, audit them, and repair them. And as I've said, there are so many alerts to repair that most people just filter out any alerts that aren't deemed critical, and they just repair the critical alerts. In our case, we add the repair tool and we add a plugin to the IDE. So the alerts, instead of going back to the developer, they go to our repair tool. Our repair tool then produces a whole bunch of possible fixes, and then it's a matter of the developer just simply bouncing from fix to fix, saying, I want this one, I don't want that one. It's sort of like a search and replace operation or a spell check operation. Imagine you have a large Word document with misspelled words, and you can just simply bounce along the misspelled words and fix the ones that are truly misspelled and not fix the false positives. So as I said, our collaborator suggested that we actually integrate our repair tool into a CI platform. And so this is how we envision that a CI will be improved by repair. In traditional continuous integration, the developer has an IDE, again, and this IDE is fronting a version control system like a Git repository or Perforce. Normally, the CI system is triggered possibly every night or possibly when a new code is committed. The CI system will then build the code, do some internal tests, produce static analysis alerts, and then the user gets to deal with the static analysis alerts. In our scenario, the static analysis alerts, instead of going to the user, they go to our repair tool. The repair tool produces a version of the code with all the problems repaired, and then it creates a pull request. So pull requests in continuous integration simply provide a new version of the code, and normally a user has to decide whether to accept or reject the new version. Usually pull requests are made by one developer, and so the other developer will have a nice interface, maybe a web interface, that lets them see the differences between the old and new code and lets them comment on it. And you can have lots of comments and discussions about why the code is this way and why the patch is this way. But ultimately, the developer's job is to either accept the patch or reject it. So ideally, the developer will accept the patch and accept all of the new repairs. Therefore, our tool has been added to CI, and therefore will catch fixes as developers are writing code and presumably introducing simple coding mistakes. So that's our solution. The big way of convincing our clients that the solution is good and is trustworthy is to do testing. So I'm going to start off with a little bit of formal verification theory about how to test things. The argument is that in C and C++, the main thing to avoid, if you want to avoid security problems, is undefined behavior. This is any code program behavior that where the standard simply says anything can happen after this point. The program might do what you expect. It might simply give your secrets to the Russians. It can do anything. Anything is possible, and nothing is guaranteed. Nothing is secure. So the rules that we're developing repairs for all prevent undefined behavior. I have two examples here, such as reading an uninitialized variable and dereferencing a null pointer. As I said, anything can happen here. Usually what happens is the program crashes, but that's not guaranteed. And the CERT vulnerability database is replete with examples of code where this happened and pwnage resulted. So our repair mechanism simply converts code that has undefined behavior into code that has an error condition. Maybe the program terminates abnormally. Maybe it pops up a dialog box. What it does is specific to the program, but our argument is that any error condition that is controlled by the developer is better than undefined behavior. And likewise, code that is not broken, if the tool says, integer overflow on line 10, but there's no problem on line 10, then we either leave the code alone or we introduce an extra check that doesn't change the behavior of the code. So we leave code that's, we leave things that are true positives behaving the same, even if we added an extra spurious check, and we only change the behavior in preventing undefined behavior. This is our guarantee that our repair will not break code, and that is critical to establishing, making it trustworthy and acceptable for use by the DoD. So for testing, we're basically testing using testing on initially 3 rules, cert rules. They also have CDBs associated with them, but we're testing these 3 rules. We're testing on 2 open source code bases. Git happens to be one of them, and the other one is Zeek. Both of these code bases have test suites. You can simply type make test. It runs through their testing process. In fact, Git has a very reliable testing process that works completely and detects and has detected any attempts of mine to, say, introduce bugs in. It gets done. It has pretty good code coverage. Zeek has less good code coverage, and not all the tests work. And the reason we're working with Zeek is because our collaborator has requested that we repair it. Furthermore, we're using the following 3 static analysis tools: CPP check, Clang Tidy, and Cert Rose checkers. These all have the critical advantage that they are free and open source, and so we can use them, do anything we want with them. So right now, our plan for the rest of the year is to work through these 5 types of tests. I'm not going to go through all of them. I'm going to focus mainly on the sample alert testing, where the idea is simply have the repair code and then manually check the repair to see if the repair is correct and if the code should be repaired. So initially, we wanted to repair and manually check every alert, but there's 15,000 alerts. Le deluge has hit us too. So what we're actually doing is we're sampling for each code base and analysis tool and cert rule. We're selecting 5 alerts at random from the set of alerts and making sure that those are correct. At least 80% of them are correct. And if 80% are correct, then we're happy. We're also doing a stumble through testing where we just simply make sure that the test mechanism does not crash. It does not prevent us, testing the entire thing. We're not, for the stumble through, we're not making sure that all 15,000 produce the correct results. We're just making sure they all produce results. But the important thing is the sample alert testing. We have several other tests here, but I don't really have time to go over them. But I'm happy to discuss them with people if, on an individual basis. So we are so far into the project for 1 year. We have 1 year more, and we've learned a couple of things. For example, the definition of if a repair is satisfactory is the important thing. We're striving to make 80% of alerts satisfactory, and what I'm going to show you now is example code from Git where this question of what is satisfactory came up. So what you're looking at is a single function from Git. And in particular, Clang Tidy complained that the CE pointer might be null. And it complained that it might be null only in this one location, even though CE is clearly referenced several times in this code. So if a developer looked at this, they would say, well, if that's true, then what we would do is we would add a null check before the statement, up here, and not actually put the null check inside this expression, replace the CE with a null check around it. However, a developer would do that, but that's because the developer has the extra intelligence to see this whole function, and that there's several that adding a check to each instance here is redundant and hurts performance. However, for our project, we're not doing that extra static analysis. We are instead trusting that Clang Tidy has given us a good picture, and that for whatever reason there's a problem in this one line of code or this one expression and not in the other ones. So therefore, we're simply suggesting that repairing that one expression is a satisfactory repair. It does repair the problem that Clang Tidy reported, and presumably Clang Tidy can later report other problems. We might do differently if we see that all these references in CE need to be fixed, but basically we are trusting the static analysis tool again. our argument is that static analysis is a mature industry. There's been tools around for 40 years, and therefore, while we can develop our own static analysis, we don't want to compete with them. We want to focus on repair, not just second guessing the tools themselves. Okay, so here's a problem we discovered from our collaborator. Actually, our collaborator was using several static analysis tools, including Fortify and CPP Check, and they're less interested in cert rules. They're more interested in MITRE CBEs. Which CBEs can we fix? So we can fix a CBE like 476, which is null pointer dereferencing. That's one of our cert rules. It maps very cleanly to a cert rule. We received a lot of data from him from the collaborator that said this line violates CBE 398, which simply says code quality. CBE 398 is simply a category CBE, meaning that it simply says there's a problem with the quality of code and gives no other information. If you look at the CBE online, it's otherwise vague. There is a specific message associated with each one, with each CBE, and we can rely on the message. But I can't repair code just because it says there's a code quality problem on line 10. There's too many different things that could represent for me to know exactly what the static analysis tool is complaining about. So we thought that we would be able to ignore the message text that each static analysis alert contains. It turns out that we can't. If they're linking to a vague CBE like 398, then we have to look at the message and examine that to figure out exactly what repair to be done. A third thing is that, as I said, we are using Clang to analyze. So we're using Clang to generate the abstract syntax tree of code so that we can properly repair it. We're also using Clang Tidy as a static analysis tool, but that's irrelevant for this purpose. What we discovered is that Clang produces very nice, sophisticated ASTs most of the time, not all the time. For instance, if I declare a typedef line, such as the one on this slide, then I get a nice breakdown of the type itself. But if I declare a variable using a fancy type without a typedef, then I don't get the equivalent AST. I get something like a single node that says it's a void star function pointer, which is unhelpful. When I talk to, I'll give a shout out to Aaron Ballman, who is a former SCI employee and is now the maintainer of Clang. And I said, is this a bug? And he says, let's just say it's a missing feature. It's a missing feature, and so it's something that we could actually add to Clang. And Clang has actually expressed interest, therefore, in us adding this feature and sending it back to Clang. And after some legal wrangling, CMU has allowed us to make this repair and send it to the Clang community, and therefore improve Clang both for users and for more researchers like ourselves. So this is us discovering a need in the open source community and working to fulfill it. Therefore, the conclusion is for this year we will have built 3 repair tools, and we will be shortly transferring it to our current collaborator. For next year, we will be extending the project to handle 10 repairs, 10 different types of repair categories, and extending to more collaborators. And there's many extensions we can do to the tool, such as adding support for more GUIs, support for more CI pipelines. For this year, we'll be supporting GitLab, and we could add, say, Jenkins or Atlassian Bamboo. Repair more types of defects. In addition to cert rules and CBEs, we could say repair MISRA rules violations. And we could use the repair tool to detect and repair other problems, such as problems with error handling or indentation. So I will thank you for this presentation. I'm leaving you with our current repair team.